A tube laser can cut a joint so accurate that the parts hold themselves together before a single weld goes down. No marking out, no grinding to fit, no jig. The trick is not the laser. It is what the machine knows about the tube before it cuts. And the last part of that is what most shops get wrong. Start with the machine itself. A flat sheet laser moves a head over two axes. A tube laser adds rotation. The tube is gripped in chucks that spin it while the head moves along its length, so the cut is a coordinated move between rotation and travel. That is why a tube laser can put a hole in the side of a round tube that is a true circle, not the stretched oval you get from wrapping a flat pattern around it. The chucks do more than spin. They center the tube. Real structural tube is not perfect. It has bow along its length, twist, weld seam upset on the inside, and wall thickness that varies around the section. If the machine simply assumed a perfect profile, every cut would drift as the tube deformed and rotated. So the machine measures. Most tube lasers probe or scan the tube before and during cutting. A capacitive or mechanical sensor touches off the faces to find where the material actually is, corner by corner, and the control shifts the cut path to match. On a rectangular section, it will also work out the corner radius, because a laser cutting round a corner has to know where the flat ends and the curve begins. The weld seam matters too. Welded tube has an internal seam that is harder and often thicker than the parent wall. Cut straight through it, and you can get a rougher edge and dross on that one line. Better machines find the seam and rotate the tube so the seam sits where you want it, usually inside the joint, hidden and out of the cut. Now, the reason people buy these machines? Coping. To weld a round tube onto another round tube, you need a saddle shape, a curve that wraps the joint. By hand, that is a template, a grinder, and a lot of swearing. On a tube laser, it is just geometry. The machine cuts the saddle profile straight into the end of the tube, so the two parts meet with a consistent gap all the way round. A consistent gap is worth more than it sounds. Weld quality depends on fit-up, and a joint with a uniform root gap gets uniform penetration. Hand-cut joints vary along the seam, so the welder has to change speed and fill the gaps, which puts in more heat and more distortion. A machine-cut joint lets you weld faster with less filler because the geometry is the same at every point. Then there is bevel cutting. A three-dimensional head can tilt, so instead of cutting square through the wall, it cuts at an angle, putting a weld preparation directly on the part. That means no separate beveling operation and no grinder time before welding thick wall sections. It also lets the machine cut miters for corner joints, so two tubes meet at an angle with faces that actually touch. The design trick that ties it together is tab and slot. Because the machine can cut features anywhere on the tube to the same accuracy as the cut ends, you can put a tab on one part and a matching slot in the other. The frame then assembles like a kit. Parts self-locate. Squareness comes from the geometry instead of from a jig, and one person can tack up an assembly that used to need two people and a measuring tape. Where it goes wrong is the end of the bar. Tube arrives in fixed lengths, the chuck has to hold something, and the last part of every bar cannot be gripped, so there is a remnant you cannot use. Nesting software fits parts along the stock length to shrink that offcut, but on short runs the scrap is real. The other trap is slugs and offcuts falling inside the tube and jamming the machine, which is why the unloading side matters as much as the cutting side. So the value of a tube laser is not cutting speed. It is that every hole, slot, mitre, and coped end is placed from the same datum, in one setup, on a tube the machine has actually measured. Fabrication time moves out of the welding bay and into the CAD model, which is where mistakes are cheap. Next episode, roll forming versus stamping versus bending, and how a shape actually gets chosen.